Hello, everybody. I am Mohanty. I welcome you all who are listening to my lectures, students all over from India. It's a great privilege and honor for me to deliver this lecture in this platform. Thank you very much for the start organizers for giving me this opportunity. What an exciting time for us in space science. We have Chandrayaan 3 mission launched successfully just a week ago. We'll have another mission which is scheduled to be launched after about 1 month called Aditya L1 to study the suns. In my lecture, I am going to tell about cosmic rays, whose origin has remained one of the biggest mystery in science since they were discovered more than a century ago. I will try to motivate you why you need to study cosmic rays. I will also tell you the status of the cosmic ray research in India since the pioneering work of Dr. Homi Bhabha and Bikram Sarabhai. So I will try to bring you the connection between the Aditya L1, our cosmic ray research, towards the end of my lecture. So let me start by introduction to the cosmic rays. So the question is, what are the cosmic rays? Yes, they are the high energy charged particles, bare atoms, no electrons. They are traveling throughout our galaxy and intergalactic space nearly at the speed of light. They bombard our Earth from all directions all the time. They consist of mainly protons and helium that constitute about 99% and 1% heavier elements such as carbon, nitrogen, oxygen, silicon, aluminum, iron, almost representing the entire periodic table with a similar composition to our sun. But there is small difference. Roughly 100,000 cosmic ray particles pass through our body every hour. They are like tiny bullets of size of 10 to the power minus 15 meter, order of one forming. What is unique about cosmic rays? Its energy. They are the most energetic radiation known to be present in the universe. They have energies over an incredibly large range, starting from 100 million electron volt to goes over 10 to the power 20 electron volt. One followed by 20 zeros. When I say 1 electron volt, it is the energy gained by an electron subjected to a voltage of 1 volt. To give you an example, energy of visible light is 1 electron volt only. Another example, the average energy of electrons in the sun's corona, as you know, where the temperature about 1 million degree Kelvin, it is about only 100 electron volt. To give you another example is radioactivity emission. As all you know, that are alpha, beta, and gamma, it's order of 1 million electron volt, which means the cosmic ray, the minimum energy is 100 times more energetic than the radioactivity emission, and the highest energy is 100 billion times more energetic than the radioactive emission. This tells us that cosmic rays has incredible range and it is mind-boggling. So the question is, how does the nature produce such high energy particles? Let's talk about the flux of cosmic rays. When I say flux, it is defined as a number of particles per unit area per unit time. So flux of cosmic rays decreases rapidly as you go to higher energy. To give one example, at energy 10 to the power 11 electron volt, which I call 100 giga electron volt, the flux is 1 particle per square meter per second, which means if I have a one detector area of 1 meter square, I have to wait for 1 second to get one cosmic ray particles. Going to the higher energy 10 to the power 15 electron volt, which you call 1 beta electron volt, the flux is 1 particle per meter square per year. Means if you have 1 meter square detector, you need to observe 1 year to get one. one particle. Now going to even higher energy, 10 power 18 electron volt, it is only one particle per kilometer square per year. That means if I want to detect cosmic rays at this energy, I need to have detectors at spread over several square kilometers. And it is not thus a prediction, it is observations. As you see in the right side, this is so-called cosmic ray spectrum. In a spectrum, in the x-axis, you see cosmic ray energy in a logarithmic scale, which spans over 12 order in magnitude, starting from 10 to the power 8 to 10 to the power 20 electron volt. Y-axis, you see the flux that changes over 32 order of magnitude in energy. What spectrum you are seeing, it is measured by detectors of different sizes, right from the low energy to the highest energies. Let's talk something about the discovery of cosmic rays. So as you know, called electroscope. Electroscope is an early device to measure the presence of charge or to measure the amount of charge. It is what you can see in the left figure. It is a glass jar and there is a rod, and in the rod there are two leaves called gold leaves, and at the top of the rod there is a disc, metal disc. When you have a charged rod, you are bringing to the disc positive charge rod, then it will induce negative charge in the metal disc, and subsequently there will be induction of positive charges. These positive charges travel through the rod to the two to the leaves, gold leaves, and since they both have same charge, type of charge, they will deflect. So the amount of deflection, what you see, that can give you the amount, that can give you the measure of the charge. In 1785, Coulomb found that electroscope can spontaneously discharge by the action of the air if you leave it for some time. Then this was confirmed by Faraday in 1835. In 1879, Crookes, another scientist, he measured the speed of the discharge that decreased when the pressure inside the electroscope reduced. So finally they concluded the direct agent is the ionized air, which is responsible for the discharge of the leaves. About 100 years later, in 1896, the spontaneous radioactivity was discovered by Henry Becquerel. In 1898, Marie and Pierre Curie, they discovered that polonium and radium undergo transmutation, generating radioactivity. In the presence of a radioactive material, a charged electroscope promptly discharges. So they thought there is a radioactivity in the surrounding. That is what is responsible for the discharge of the electroscope. Yeah. Now, there are a lot of stories in between. I am not going to go all into detail, but let me come to the climax, how the cosmic ray were discovered. On August 7, 1912, Victor Hess, a 29-year-old young man, he flew on a balloon to an altitude of 5,200 meters, taking two electroscopes with him. In fact, he has many such attempts, but some attempts he has succeeded, some attempts he has not succeeded. But in this attempt, he flew to the maximum altitude. So he carried two electroscopes, and what he see, the measurements, that initially the ionizations, what you see in the left side plot, that was initially there are no increase, but after some altitude, it start to increase. Then he concluded the increase in the ionization with height is due to a radiation which is coming from the above. So it made him to think that the radiation is not terrestrial, it is extraterrestrial radiation. Another scientist, Millikan, who was also working on this subject, and who is also known famous for oil drop experiment. He named this radiation as cosmic rays. However, later only it was established they are not rays. Those are the charged particles. Victor S. got the Nobel Prize discovering cosmic rays in 1936. In fact, there are several elementary particles which were discovered from cosmic rays till the invent of particle accelerators in 1950s. So it gave birth to the element and particle physics, but I don't have time to discuss all of them. But I will give only one example: discovery of the first antimatter, that is called positron. In 1932, while watching the tracks of cosmic ray passing through his cloud chamber, Carl Anderson discovered that antimatter in form of electron. You can see the picture right side. And later it was called positrons. Because this work he submitted to a journal called Physical Regulator. The editor suggested him to the name positron. So basically, let me explain a little bit about the cloud chamber. Cloud chamber is an instrument. It contains supersaturated vapors. Whenever the charged particle is passing through that supersaturated vapor, then it forms a ionizing radiation. It ionizes the gas and leaves a track. Okay? So the bending of the track due to the magnetic field in this cloud chamber, that can tell you what type of particles. So in fact, before it was discovered by Carl Anderson, Paul Dirac, who had proposed it in 1928 mathematically. So this particle and antiparticle. The antiparticles are of the same mass but opposite charge. When they collide, they will annihilate. They can produce energy like photons. Interestingly, the Carl Anderson shared the Physics Nobel Prize in 1936 with Victor S. Let's discuss about the origin of cosmic rays. Origin of the cosmic ray has remained a long-standing problem since their discovery more than a century ago. The main reason is cosmic ray charged particles. So when they travel in our galactic or extragalactic magnetic field, they deviate from their original path. So then you cannot trace back to their origin by observing their direction on the Earth. So the question is, how does the nature produce such high energy particles? That has remained a mystery so far. However, there are beliefs and there are some possible sources. One of the possible sources is the particle acceleration in supernova explosion. As you know, supernova is a massive star. When it comes to the end stage, exhausted with its nuclear, fist, then it explodes. So this could be the possible mechanism for producing such high energy particles. So in one supernova explosion, the energy released is order of 10 to the power 44 joule. If 10% of the supernova explosion goes to the acceleration of cosmic rays, it can maintain the required energy of cosmic rays if one supernova explosion occurs in our galaxy in 30 years. Let's see the cosmic rays when they enter inside our solar system. Cosmic rays are produced outside the solar system. They travel in the intergalactic space, interstellar medium. When they enter into our solar system or interplanetary medium, there is a magnetic field in the interplanetary medium. This is the magnetic field which is produced by the sun. But the magnetic field of the sun that extends very, very far, even beyond the orbit of the Pluto. So since cosmic ray charged particles, they are affected by this magnetic field. However, only the low energy cosmic rays affected. High energy cosmic rays, still they can continue to travel in their original directions. And particularly cosmic rays of energy below about 100 GeV or 10 to the power 11 electron volt, they are affected by the interplanetary magnetic field. When cosmic rays enter into the Earth magnetic field, then let's see what happens. Earth has a magnetic field, as all of you know. Its magnetic field is produced by movement of molten iron and nickel in the outer core. Because of there, it produces a current, and the movement of current produces a magnetic field. And this magnetic field extends more than 100,000 kilometers into space. So when cosmic rays entering in the polar regions, where the magnetic field lines are parallel to the magnetic axis, and cosmic rays process in parallel to the magnetic field lines, they experience less Lorentz force, as all you know. But when they enter in the equatorial regions, the direction of the cosmic rays is perpendicular to the direction of the magnetic field. So there will be a maximum Lorentz force. Therefore, the cosmic rays find an easy path in the polar region than the equatorial region. So if you are in the polar region, you will have a maximum cosmic rays. If you are equatorial region, you will detect a minimum cosmic ray. So this effect, which is dependent on the latitude, and the cosmic rays increases with the increase in the latitude. This is called latitude effect. Though earlier by Milkan, it was thought those are rays. With this observation, it was concluded that cosmic rays are charged particles because they are affected by the magnetic field. So what happens when cosmic rays enter into the Earth atmosphere? So when the cosmic rays enter in Earth atmosphere, they interact with the nuclei of air molecules, such as nitrogen and oxygen. Then by this interaction, they produce a cascade of particles, or called a shower of particles. At the observational level or the ground level, you have a numerous of particles, which include photons, which is called gammas, then electrons and positrons, antiparticle of electrons, muons, and so on. And these particles are spread over 10 meters square to even kilometer square distance, depending on the energy of the primary cosmic rays. If the primary energy of cosmic ray entering into the Earth atmosphere is higher, then that will spread in a larger area in the ground. Also, neutrinos, which are neutral particles, they are also produced in the cosmic ray interaction in the Earth atmosphere, but they are weakly interacting in the matter. Most of these neutrinos which are produced, even they can pass from this side of the Earth to the other side. Let's see the cosmic ray observation in space and ground. So you can observe cosmic rays before they enter into the Earth atmosphere. So then this cosmic ray observation in space is done by satellites and balloons. And this cosmic ray observation is direct because once they enter, it produces secondary particles. But however, there is a limitation observing cosmic rays in space, because space there is a constraint to fly the detectors of more than like 1 meter square. So at a higher energy, about to 10 to power 14 electron volt, then you have to rely on the observations in the ground. The ground observations, as I mentioned, you cannot observe them directly, but you can observe that by observing the secondary particles which are produced in the showers. So this observation is carried at different altitudes from the top of the atmosphere, like in the mountains and at the sea level, even in the underground. Let me give example of some cosmic ray experiments located at different locations in space or the ground. One of the example called alpha magnetic spectrometer. This is located at International Space Stations at 400 kilometers. And there's another experiment called dark matter particle explorer at 500 kilometers, again in space. And there is a balloon experiment called CREAM. It was launched from Antarctica. And there are detector arrays which are at different mountain altitude. For example, one array called Tibet S Gamma in Himalayas. And this is a grade 3 experiment in UT, which I am going to talk more detail about it. It is located at 2.2 kilometers, and there are an experimental cascade at the sea levels. And if you want to detect the highest energy cosmic rays or ultra high energy cosmic rays, you need much bigger detectors, because in the middle panel, what you see, it is less than 1 square kilometer arrays. So to detect highest cosmic rays, the scientists have designed detectors which are spread over even 3,000 square kilometer. One example is called Piraeus Observatory in Argentina. So it is, the area is almost like nearly 5 times bigger than the area of the Mumbai city. Another similar experiment called telescope array in Utah. And even scientists have designed detectors to detect cosmic rays, or it's neutrinos under ice. There's an experiment at South Pole called Ice Cube, and the detector has gone up to 3 kilometers deep inside the ice. Let me talk a little about the cosmic ray research in India. We have a very long legacy since the 1940s. The cosmic research in India was pioneered by D.M. Bose, P.S. Gill, Dr. Homi Bhabha, and Dr. Vikram Sarabhai. So Vikram Sarabhai, in fact, worked on cosmic rays, which was part of his PhD thesis at Indian Institute of Science with the supervisor of C.V. Raman. He continued his research at Physical Research Laboratory with his students. Homi Bhabha, he started TIFR in 1945, and then he started the cosmic ray research at TIFR. He encouraged several groups in TIFR to do the cosmic ray research. For example, at Kolar Gold Field, KGF. Also, he set up the cosmic ray laboratory in Uti in 1954. Let me go to the latest cosmic ray experiment that is called GRACE 3, which is located in Uti. This is an altitude of 2,200 meters. Uti, most of you know, it is a tourist place. So this is what you can see here. This is the view of the GRACE 3 experiment. GRACE 3 stands for gamma ray astronomy at beta electron volt energies, 10 power 15 electron volt energies. So this GRACE 3 experiment contains 400 plastic scintillator detectors. Each of the white conical structures, what you can see in the picture, they are the scintillator detectors. So those are designed, as I mentioned, cosmic rays produces a shower of secondary particles, include electrons, muons, and photons. And these scintillator detectors are designed to record these secondary particles. And we have another detector called muon telescope. It is 560 meters square. I will talk in the next slide. So let me discuss how do you detect these high energy particles. So this is a scintillator detector. This is made of plastic. We are using for the detection of these secondary cosmic ray particles. In the left side figure, you can see whenever a charged particle passing through this detector, this is a conical structures. Inside we have scintillators, and everything is enclosed. Only the charged particle they can penetrate inside it. There are no outside light coming inside, and whenever the charged particle passing through the scintillator, it produces a flash light or photons. A small fraction of this light that is emitted, because the light emission occurs all directions, and that come out of the scintillator, and some of them can reach to the photo device called photomultiplier tube, and it works in the principle of Einstein's photoelectric effect. That means the photons of light get converted to electrons, which is called photoelectric effect, and it produces a signal or current. That is what we detected. So these plastic scintillators are also developed in the produced in the cosmic ray laboratory in Ooty. So now coming to the muon telescope, it consists of 4 stations with total 16 modules, and it employs 3,712 proportional counters. As I mentioned, like electrons and gammas, muon is another component in the cosmic ray showers. But the beauty of the muon is that they are more penetrating than electrons and photons. So if you want to detect the muons in the showers, then if you put observer shielding, then electrons and photons, they can be shielded, then you will have the muons. So this is what we have done. What you can see here in the left bottom picture, this is inside the view of the one of the muon telescope station. There are 4 modules in the stations. There are 2 modules in the front and 2 modules in the front, and each module consists of the proportional counters. Proportional counter is a gaseous detector. Means whenever charged particle enter proportional counter, it can ionize the gas and produce a signal. So there are layers of such proportional counters which are arranged in 2 orthogonal directions. Whenever the cosmic ray secondary particles that is falling above the muon stations, and since there is a concrete above these counters, they observe these soft components, electrons and photons, the muons which are penetrating. Even the muons can penetrate kilometers on the ground. So you can detect the muons. Okay. And also not only that, you can detect the direction of the muons because of the arrangement of these proportional counters in the 2 perpendicular directions. The most unique thing is that it records 4 billion muons per day, and this is the largest muon telescope in the world that allows to certain things which is unique. We are in the process of building another muon telescope of similar to the existing one. So that will increase the area 560 meters square to 1130 meters square. So again, it consists of about 3,776 proportional counters, which all proportional counters are fabricated in this cosmic ray laboratory in Ooty. These are some of the pictures. Now this is partially completed, and we are hoping it to make operational within another year time. Let me change to another topic that is related to our study using the muon telescope. It's called solar phenomena and space weather. This is a very important topic for the societal point of view. So let me introducing what is space weather, what is solar phenomena. As you know, the sun is not quiet all the time. It becomes sometimes active and sometimes it become very quiet. And this activity has a 11-year period that we call 11-year solar cycle period. During the active period, the sun emits, sun produces a lot of events, and one of the event called solar flare. And when the energy in form of light, visible photons or X-rays comes out of the sun. And another kind of event called coronal mass ejections, when the mass and magnetic field from the sun comes out. It's a huge amount of mass which comes out, which even millions, even if equivalent to the mass of millions of Earth. So once this coronal mass ejection leaves the sun and it enters to the interplanetary space, it expands, then it takes about 1 or several days to reach the Earth. And our Earth, as you can see in the right side picture, it's very tiny. Of course, it is not up to the scale, and it has a magnetic field, as I mentioned. But however, because of the pressure due to the so-called the solar wind, which is flowing all the time, it has a different shape. The day side of the magnetosphere get compressed and night side become elongated. So whenever this coronal mass ejection or the cloud of the plasma, which is coming to the Earth, and that is interacting with the Earth magnetosphere, what happens? Because when it is not there, the Earth is protected by this magnetic field. Lots of the charged particles which keep coming from the sun, they cannot enter into the Earth. It's a protective shield. But when this cosmic ray ejection, coronal mass ejection comes, it can interact with the Earth magnetic field, because the coronal mass ejection has magnetic field, and then by these interactions, it can weaken or it can open up the Earth magnetic field. That times the low energy particles which cannot come because of protect, they can enter in the Earth atmosphere, and that generates the space weather, and that can also trigger something called geomagnetic storms when the current in the Earth magnetosphere increases. So what are the impacts of space weather? Space weather has a significant impact on the technological infrastructure of the Earth. Example, they can disrupt radio communications, they can disrupt satellite communications, they can disrupt GPS communications, and they can disrupt even the navigations. More importantly, also they can disrupt the electrical grid on the Earth. Let me example how they can disrupt the electrical grids. As you know, you have seen the electrical grids. The current is carried by cables, and they are separated. But whenever during these such events, large amount of current which is passing into the atmosphere, these are mainly the charged particles, and the cables in the high voltage lines, they are separated, and the air is an insulator. But whenever charged particle passing, then the insulation the air become conducting. By the process, then they become short circuited. Because of that, the entire high voltage line or the power grids can be disrupted, affected, and this happened also in the past. Let me give you one more recent example how the space weather or this space weather events have affected our technology. One example, very recent example, which occurred 4th February last year. The space company which launched 50 new satellites on 4th February, on 3rd February. But there is a solar storm which occurred on 4th February. So this Starlink satellite which are intended for giving the internet connectivity, satellite connectivity to the world. So then these are the small satellites. So whenever this thing happens, they are initially launched to about 200 kilometer from the Earth to a parking orbit. The intention is that if some satellites helps to satisfy the requirements for testing, they can be dragged into the atmosphere by itself. And the final aim was to launch them to a launch them to the final orbit about 400 to 500 kilometers. But unfortunately, when they are in the parking orbit, then the solar storm came, and during that time, what happened? They are actually little above the atmosphere, where the density of the air is very low, and because of the solar storm injected a lot of particles into the atmosphere. The density of the particles increased, and then the these Starlink satellites, they are within higher density of the atmosphere, and there's a dragging effect happened, and that dragged down these satellites to the earth and destroyed 13 new satellites. And this is, in fact, this was not a major solar storm, it was a minor solar storm. So you can think of the consequence of the space weather events. In this context, I am going to explain one interesting event which was measured by our Muon telescope. On 22nd June 2015, there was a massive coronal mass ejections which reached the Earth. That time, what happened? We identified this based on the data which are taken by NASA satellite at the fast Lagrangian point. At that time, the solar wind which is coming, the speed increase. That is the identification of coronal mass ejection. You can see in the left plot. Suddenly it is jumped from 400 to 700 kilometers per second. Same time, the magnetic field also increased, and the magnetic field, that is the Z component of the magnetic field, which is opposite to the orientation of the Earth magnetic field, it becomes south. That means it is something happened. But when we looked at the muon data, we saw for duration of 2 hours there is an increase in the muons, and it has a almost similar shape as the BZ component of magnetic field. And when we inverted, we found a very strong correlation. So this made us to think that the coronal mass ejection magnetic field is responsible for producing the cosmic rays. The hypothesis was the magnetic field they reconnected together, and that weakened the Earth magnetic field. That time the cosmic rays, which are low energy, which are shielded by the Earth magnetic field, they because of weakening Earth magnetic field, they could come inside and producing more muons. And this, as I said, the muons are produced by interaction of cosmic rays in the Earth atmosphere. So this result we published in a journal called Physical Evaluator. By the name of the paper was Transient Weakening of Earth Magnetic Field brought by cosmic ray burst. So once we published, it got a lot of attention worldwide. There are more than 1,000 articles published in reports in many scientific reports, and in many newspapers. In fact, one more interesting thing, as we answer, what is the consequence of the solar storms or space weather? So how do you protect the Earth? Because we are fully dependent on the technology and the society. That means you need to know them in advance. So far, lots of effort has been. There are some progress, but still we have a long way to go to accurately predict the arrival of the solar storms. But one of the one can do using the cosmic ray muons, because cosmic rays are travel at the speed of the light. Before the solar storm come to the reach the Earth, which takes about 1 to several days, the cosmic rays which travel at speed of light, they can connect instantly to the Earth, and they can bring the signature of the solar storm or coronal mass ejections. So this is a study, and it can give you a advance warning 8 to 10 hours. And this is some study which we are currently doing. Now, let me come to the connection between the DES-3 experiment, which is on the ground, and the Aditya L1. Of course, you will hear more lectures about Aditya L1, but here let me tell you how these two missions, two observations are complementary. So, if you have a fast availability of data, solar wind data at Aditya L1, Aditya L1 is going to be placed at a point called fast Lagrangian point, which is about 1.5 million kilometer from Earth. It is in between. It is in between sun. It is along the sun and Earth line. So this will be, once you can get the data from Aditya L1, that will help to useful for prompt analysis of transient events which detect at the ground by experiment like GRACE-3. So there are some remote sensing data from Aditya L1 that can be measured instantly once a solar storm like coronal mass ejection occurs in the sun, and that will be very useful to alert the precursor event which can be detected by GRACE-3. So to tell you, Aditya L1 data is important as complementary information. Same time, the ground-based observatory could provide the detailed understanding of large-scale magnetic structure and evolution of CMB. So we are all excited for the launch of Aditya L1 missions. And GRACE-3 has been running for last 2 decades, and it will continue to run. Let me change the topic. How this cosmic rays can be also very useful for the society. One of the things which are very emerging called muon tomography. You all would have heard about different tomography, how you image, you image, for example, bones using X-rays, then you have CT scans and so on. But very interestingly, you can use muons to the tomography, which can not do by X-rays or the scans. And one of the applications is, for example, to know the voids in the pyramids or mountains. So this is something which has been already successful to identify the hollows or voids inside the pyramids, inside the Khufu pyramid or Great Pyramid. So before I proceed, let me tell you the technique how do you use muons, because as I mentioned, muons are coming from space all the time. They are present, and they are very penetrating. They can penetrate 100 meters to even kilometers inside the ground. So if the muons, depending on the density of the matter, they can penetrate. If you have a higher density, they can penetrate less. They get absorbed. So by comparing, once, for example, in the left bottom side figure, you can see here, if a muon passing and there's a hollow cavity inside the pyramid, then it will come across a less density. Then you will have a less absorption of muons. But in the other directions, when there are no, where there is no hollow cavity, you will have less absorption. So by getting a map or image of the muons and detect them, you can find out which has higher density, which has lower density, of if there is a hollow inside. So this is one application, and another interesting application to know the volcano eruptions before the wherever this eruption is there, as you can see in the top right figure, that place where the magma is, that place you have a lower density. Okay. By the same principle, one can find before it erupts out, even even several days or several months before the eruption occurs, then there is a structure found there with a very low density, and by making the muon imaging, you can find out, yes, there is something, there is a eruption which is going to happen. And then one more example of the muon tomography, that is not just based on the absorption of muons, but based on the scattering of muons. So muons, when it passes different material, it has a different scattering. If the density of material high, you have higher scattering. So then by measuring the scattering angle in different material, you can find out what it material is. And you can see in this figure, then for example, is a muon passing the iron block and passing a uranium block. Iron block, which gives a less scattering angle, and uranium block, it will give a higher scattering angle. So that can tell you to identify different material. For example, the cargoes or something we are tracking. So this muon tomography can be used to identify, what is the material inside the cargo. Okay, or even you can use this muon tomography, even what is there inside the treasure, and what kind of, whether it's a gold, whether it's a, some different ornaments, because they varies with the different densities. So it has a useful applications, and this muon tomography becoming very very popular now. People started applying them for different purposes. Yeah. So I think I have now come to end of my lecture. So now thank you all for listening to my lecture.